Hello, I'm Lisa Tucker-Kellogg from the Duke-NUS Medical School in Singapore. Today I'm going to describe my research on pressure ulcers, looking at what goes wrong to cause poor healing and delayed healing in muscle layers. I declare that I have no conflict of interest. Pressure ulcers are classified as chronic wounds because they often fail to heal within an expected time frame, but there isn't much known about why they heal poorly. This project is asking whether there's something about pressure that makes the wound more hostile to regeneration. Does pressure make the wound worse off in some way, or do pressure ulcers only have poor healing because of some other setbacks or complications, such as re-injury if pressure is reapplied, bacterial infection, or diabetes, etc.? Here are my hypotheses. Hypothesis 1, pressure ulcers will heal poorly regardless of complications, provided we look beyond just the skin. Hypothesis 2, we'll see something wrong immediately after the pressure. In informal descriptions of chronic wounds, people often say that the problem is too much inflammation for too long, or the wound stays in an inflammatory stage for too long until switching to the granulation phase. My hypothesis says something different, that the problem will be apparent from the outset, earlier than that informal timeline. Hypothesis 3 is to answer the question of where slough comes from. Slough is the shedding of dead material from a wound. Slough can be thick or thin, hard or soft. Pressure ulcers are known for having a lot of slough. But what does the slough indicate if there's no infection or biofilm? Hypothesis 3 says the wound will still have slough even under aseptic conditions, and it will come from a failure of the immune system to perform phagocytosis. Phagocytosis is when immune cells chew up things that don't belong there. Next, we'll need laboratory experiments. Mice have loose skin. At the scruff of their neck, it's called the dorsal skin fold. The dorsal skin fold has multiple layers. There's dermis and epidermis, which are the skin, a layer of fat called dermal white adipose, a thin layer of muscle called the panniculus carnosus, and finally some connective tissue called loose areolar tissue. A pair of magnets gets placed over the dorsal skin fold in cycles of 12 hours on, 12 hours off. This creates a region of death in all the layers, which makes it a Category 3 pressure ulcer. This is a small wound, just millimeters, but it allows us to study the interplay of tissue types. We're particularly interested in the muscle tissue in the lower layers, not just the skin. For comparison to human pressure ulcers, note that people do have a panniculus muscle layer in the heel, and the heel is one of the most common locations for patients to develop pressure ulcers. To learn more, I do have a talk about the panniculus layer. So our results show that when we use aseptic conditions with no bacteria in the cage, the bedding, the air, the water, then the wound healing outcomes are still quite poor for pressure ulcers. Here's a Gantt chart, like a checklist of wound healing milestones, comparing normal versus pressure ulcer healing. The normal wound has a rapid succession of steps, one part completed within 3 days, some steps at 10 days, and then the wound is fully healed by 16 days. In contrast, the pressure ulcer at every step either has delays or outright failure. The normal comparison wound on the left is created by injecting a little bit of a snake venom called cardiotoxin into the skin fold at the scruff of the neck, which kills a tiny region of muscle tissue. You can see black arrows pointing to the muscle layer. On the left are lots of dark purple dots, which are immune cells swarming in to digest the dead tissue. The pressure ulcer on the right is thinner because it used to be compressed. But what else is different? Let's zoom in look at the immune cells. We can see the left has a huge number of the dark purple dots, and on the right side, the pressure ulcer has no intact immune cells. There are some dead fragments of immune cells in the fat layer, which is the white blobs above. There are some dead fibroblasts in the connective tissue below, and we do not see the normal rush of immune cells infiltrating into the dead muscle. Here's another cross-section of the wound taken later, after there's been more time for other cells to regenerate, and they push up on the dead tissue, which is still there. It's been sitting there all this time, and phagocytosis did not occur. Eventually, the new regeneration pushes it up, and what we're seeing here is the process of sloughing. So what's coming off at the top is not just flakes of skin, it includes fat and muscle. You can see the muscle, it's this red-colored layer. On the left side, in the viable tissue, the muscle is sitting where it belongs, under the fat. The dead muscle on the right has been pushed up, and in the process of being pushed up, the layering structure has been distorted and bent. The necrotic tissue then comes off as an eschar. That's necrotic, it's correct to call it necroslough, and underneath there's granulation tissue that has not yet formed layers. For it to form layers will be an extra challenge because the sides of the wound that have good muscle are bent upward, and the middle of the wound is going to try to regenerate in a flat sheet. When we follow that out for 40 days, 90 days, this is what it looks like. On the left, we see healthy muscle regeneration after the snake venom injury. On the right, it's after a pressure ulcer. The right is disorganized, diagonal, wavy. And when that muscle tries to contract its fibers, this will not be a healthy situation. A lot of it is probably going to die. So let's review what we've learned so far. Hypothesis 1 is that pressure damage is worse than other types of damage. Indeed, the pressure ulcers did heal poorly even when there was no infection or any other complications. What that means is that fighting infection by itself will not be enough to restore healthy healing. Fighting other complications like glycemic control will not be enough by itself to normalize healing from a pressure injury like this. Something pressure-related is going wrong even in subjects that are young and healthy with no reloading and no bacteria. Hypothesis 2, that problems will start immediately. That was true. What we saw was actually kind of a wacky injury response because there were no immune cells, no phagocytosis. It's not just a problem of too much inflammation lasting too long. The early stage garbage collection did not occur. The immune cells instead died. The reason we know they died is because they left behind some molecular markers that I didn't have time to show you. So in light of what happened to the immune cells, it's no surprise what happened for hypothesis 3. The phagocytosis failed and the dead tissue turned into slough. So now we know that when we get rid of all of the usual suspects, the textbook causes of poor wound healing, we get rid of bacteria, viruses, fungi, old age, reloading, diabetes. These pressure ulcers still had poor healing. The timeline of healing was slow. The final tissue was malformed or it had holes. This work is the first I know of that studied deep pressure ulcers under aseptic conditions. We also have other experiments not focused on in this short talk describing what does cause the poor healing and how to treat it. As a teaser to entice you to come back, I'll tell you that the injury response process can be normalized if we knock out myoglobin. The oxidative stress goes down and the number of immune cells goes up closer to normal. Also, we can inject a drug to target the myoglobin iron, and that will also improve the oxidative stress, improve the number of immune cells, and save tissue from dying in the edges of the wound. So the drug treatment can salvage the viability of the tissue edges, even though we don't give the drug until after the pressure has finished. I hope you'll come hear our other work. The takeaway message from this first talk today is that there is something extra damaging about pressure injury. It gives us dead tissue that makes the immune cells go away instead of the immune cells making the dead tissue go away. I'd like to thank the excellent scientists I've been privileged to work with on this project, especially Jana Nasir and Hans Heemskirk. I'm grateful to my funding agencies for supporting this work and to you for your attention. I hope you'll visit our website.